In this lecture, I am going to illustrate the use of complex analysis to evaluate integrals involving real functions. Okay. So, we have seen that integrations in the complex plane can be carried out very easily using the residue theorem. Okay. And now, all you need to know in order to evaluate the integrals is the location of the poles. Okay. And then you can just use residue theorem to do the integrals. Now, what we are going to do in today's lecture is to show how this theorem can be used to evaluate integrals involving real functions. Complex analysis is a very useful tool in science and engineering, and you know even though you say that all the natural phenomena, natural observables that you see are they all involve only real variables. However, sometimes going into the complex plane helps in actually evaluating some of the integrals. So, I will do two types of problems today. So, the first type of problem, okay, is the kind of integral of this form. So, the first application is integrals of the form integral 0 to 2 pi f of some function of cos theta and sin theta d theta, okay, some integral of this form. Okay. And the second application I am going to do is integrals of the form. So, I will say limit as a tends to infinity integral minus a to a f of x dx. Okay. Now, these are so what I mean is you have a in the first case you have a function of cosine theta and sin theta, and then you have d theta. In the second case you have a function of x dx which you are integrating from basically minus infinity to plus infinity. Okay. And both these integrals are in fact the second integral is called the Cauchy principal value of f of x. Okay. So, both these integrals are they are seen very widely, okay, and for this reason we will see how going to the complex plane makes evaluating these integrals much easier. Okay. So, what the idea is that you take your integral. Okay. So, suppose I call the integral. So, let me say integral in real space, I will call it I. Okay. So, the idea is the following. So, you take your I and you convert it, okay, using you convert it to an integral dz. I will just say f of z dz, okay, over some contour. Okay. And so once you convert your integral in real space to a contour integral in complex plane, okay, then you can do it easily, and then you can actually carry out the integrals easily. Okay. So, now let us look at the first case, and then we look at the second case. So, let us take an example. So, suppose I take integral d theta, let me take 10 minus 6 cosine theta, okay, integral 0 to 2 pi. Okay. So, suppose you have an integral like this, okay, then I can write, then what is done is you make the substitution. Okay. So, integral 0 to 2 pi. So, if you think in terms of complex variables, and if you imagine that theta is the polar variable, okay, if you imagine that theta is the polar variable for the complex number in the complex plane, then this 0 to 2 pi looks like an integration over theta. theta, and it goes from 0 to 2 pi. So, its theta is going through this loop. Okay. However, you notice that there is no r. Okay. So, what is done is you make the following substitution: z equal to e raised to I theta. So, z equal to e raised to I theta. What will dz become? Dz, okay, let me write it here, dz equal to, now derivative of this with respect to theta will be I e raised to I theta d theta, okay, which is equal to I z d theta. Okay. So, what we have is d theta equal to dz divided by I z. Then what you do in general, okay, in this case I had only cosine of theta, but in general if I had cosine theta, I will write as e to the I theta plus e to the minus I theta divided by 2, okay, which is equal to z plus, now e to the minus I theta is nothing but 1 by z divided by 2. Okay. And so, this becomes equal to z square plus 1 divided by 2 z. Okay. Now, what about sin theta? Sin theta, in this case we do not have sin theta, but if you had sin theta, then sin theta would be e to the I theta minus e to the minus I theta divided by 2 I. Okay. So, this is z minus 1 by z divided by 2 I, that is equal to z square minus 1 divided by 2 I z. With all this, with this simple substitution, okay, what we will see is we will convert this to an integral over z, okay, and the contour of z will be exactly this contour. So, if this is the xy plane, this is the contour over which we are going to do the integral. So, starting from here and going all the way around to here. Okay. So, let us now evaluate the integral. So, if we call this integral I is equal to so, this is a integral over a closed contour. Now, d theta is dz divided by I z, and what you have is 1 over 10 minus 6. Now, cosine theta I can write as z square plus 1 divided by 2 z. Now, you can write it out. Okay. So, this becomes integral over c dz divided by I, okay, and what you have is 10 z minus 3 z square plus 1, and I can take the what I can do is I can take the I outside, and 1 over I I can write outside, and I have a closed integral dz divided by, now what I have here is minus 3 z square plus 10 z minus 3. What you need to do is you need to write this in terms of fractions. Okay. So, in this case it is quite straightforward. So, I can write this in the following form. So, let me take that integral. So, I will write it as 1 divided by I, and then what I have is I have integral dz divided by minus 3 z square plus 9 z plus z minus 3. Okay. So, I can write this as equal to 1 over I integral dz over z minus 3 1 minus 3 z square, no 1 minus 3 z, okay. So, minus 3 z, z minus 3 plus 1 z minus 3. So, 1 minus 3 z. Okay. So, now we got it in a form where we can use the residue theorem. So, this is integral over a closed contour. Okay. Now, notice that the contour that we have is the unit circle. Okay. Now, z equal to 3 1 2 3 it corresponds to this point. So, this has two poles z equal to 3 and 1 minus 3 z equal to 0 or z equal to 1 by 3. Now, z equal to 1 by 3 is somewhere here. So, z equal to 1 by 3 and you have z equal to 3. Now, this is z equal to 1 by 3, this is z equal to 3. So, we have these two poles and clearly you can see that in this contour integral the only pole that matters is z equal to 1 by 3 because that is the one that is inside the contour. Okay. So, what this becomes is the following. So, it becomes so I will write 1 over 3 I, okay, dz divided by z minus 1 by 3 and I will write 1 over z minus 3 in the numerator. Okay. So, I am just writing it in this way. So, what this gives you will give me 1 over 3 I. Now, this is this contour is a unit circle. So, this is the only residue that will matter. So, it will be into 2 pi I. Now, the remaining function is 1 over z minus 3. So, 1 over z minus 3 evaluated at z equal to 1 by 3. So, that is into 1 over 1 by 3 minus 3. 1 minus 9 is minus 8. So, and 3 will cancel, I will cancel. So, what I will get is minus pi divided by 4. Oh, okay. No, there should be a minus here. There should be a minus sign here. So, it is z minus 1 by 3 that pulls off a minus sign. So, it will become plus. Yeah. So, it is plus pi by 4. Okay. So, this is an example where we converted a real integral, okay, into an integral over a complex, over the complex plane, and then we used residue theorem to evaluate that integral. Now, the second kind of integral, okay, which is done using the complex plane methods, has to do with integrating typically from minus infinity to infinity over the real line. Okay. So, what is done is you write that integral from minus infinity to infinity in the following form: limit as a tends to infinity, integral minus a to a f of x dx. Okay. So, let us take an example of that. Okay. So, for example, you could have example f of x is equal to 1 over 1 plus x power 4. Okay. So, you could take something like that, or you could take x power 5, or you could take any polynomial in x. Okay. And I am taking this form, okay, just to illustrate what you can do. Okay. You could take any function of x. Okay. So, the method will remain exactly the same. The idea is the following. So, what you have is, if you imagine the complex plane and you imagine the x as the real line. Okay. So, what you have is from minus a to a, okay, and then you will let a go to infinity. So, you have this integral, and so what we are going to do is to make a contour that looks like this. Okay. So, make this contour. So, see. So, what you are going to say, if this integral is called I, okay, we are what we are going to do is to write I as integral over a closed contour of f of z dz, okay, minus integral over this open contour C, okay, of f of z dz, okay, and this contour C, okay. So, the contour C, now let me call this entire contour as C0, okay. So, we will call this C0, which is the entire contour, okay. So, the idea is this, yeah. So, the integral over the entire contour can be written as an integral from minus a to a, okay. So, I will show it this way. So, I can write this as sum of this integral plus sum of this integral, okay. So, the integral over the entire contour, okay, C0 can be written as a sum of integral from minus a to a and the integral over C, okay. So, then the integral from minus a to a can be written as the integral over the entire contour, that is C0, okay, minus the integral over C, okay. So, let me emphasize here that C0 is the closed contour, okay. So, now and then what we will see is that you can easily do these two integrals, okay. So, let us look at this. So, I is equal to integral. So, in this case I can write it as 1 over 1 plus z power 4 dz minus, so this is over a closed contour, okay, the closed contour is C0 minus integral over C. Now what is the contour C? So, you have 1 over 1 plus z 4. Now, if you look at C, okay, so this contour C corresponds to a e to the I theta, and you take theta from 0 to 2 pi, theta goes from 0 to 2 pi, less than pi. So, I can write this in the following form. So, the idea is to write z in this second integral, okay. So, in this integral, only in this integral I will make the substitution z equal to a e to the I theta, okay. Now, dz equal to I well, okay. So, I will write a I e raised to I theta d theta, okay. And so then this second integral becomes the following. So, integral over C dz over 1 plus z square, okay, is equal to, now we have limit as a tends to infinity, okay, integral, now you have 0 to pi, okay, and what you have is dz is I a e to the I theta d theta divided by 1 plus a e to the I theta. So, a raised to 4, I can just write this as 1 plus a power 4 e raised to 4 I theta. In this case you can easily see that when a goes to infinity, okay, the denominator will become very large because it has an a power 4 here, okay. So, the denominator will actually go to infinity, okay, and so but the numerator has only a. So, the numerator will go to infinity much slower than the denominator. So, actually this integral equal to 0. So, in the limit as a tends to infinity, this integral will be exactly 0, because the denominator has a power 4 and the numerator has I has only a. Okay. Now, I have not shown this formally, but you can easily work this out and show, okay, that as a goes to infinity, okay, the denominator will go to infinity, okay, and you know, even when you so then this integral will go to 0. Now, you can actually work out this integral if you want, okay. You can actually solve this integral and you can actually show that indeed this is true, that this integral goes to 0 in the limit as a tends to infinity, okay. But I am not going to bother doing that, okay, because in some sense it is fairly obvious, okay, that this integral will actually go to, this integral will go to 0. Now, in some cases this integral might not go to 0, okay. For example, if you just had a e raised to I theta in the denominator, okay, instead of a power 4, if you had 1 plus z, okay, then clearly this integral would not go to 0 in the limit as z goes to infinity, okay. Now, in that case you have to actually evaluate this integral, but in this case it is fairly straightforward that the integral will go to 0. I can write I as a simple contour integral, okay, 1 over 1 plus z power 4 dz, okay, over the closed contour of radius a. Okay, now z power 4. So this has, you can easily write where the poles are. So poles are at z power 4 equal to minus 1, okay, and if you write so then so this is the fourth roots of negative 1, okay. So and these will be at the following points. So so if you want to take the fourth root of minus 1, okay, then what you do is you write this as e to the I pi, okay. Z power 4 is e to the I pi or e to the 3 I pi or e to the 5 I pi or e to the 7 I pi, okay. So z power 4 is minus 1, I can write minus 1 as e to the I pi, e to the 3 I pi, e to the 5 I pi, e to the 7 I pi. I deliberately wrote these 4 things, okay, because now if I take or so what does this imply, z is equal to, so if z power 4 is any of these, then z should be this raised to 1 by 4. So that is e to the I pi by 4, e to the 3 I pi by 4, e to the 5 I pi by 4, e to the 7 I pi by 4. So these are the 4 roots. So notice that all of these, pi by 4 is 45 degrees. So the roots are basically located on the unit circle. So x, y. So the location of these roots, okay. So if this is a unit circle of radius 1, if you draw the unit circle, this is 1, this radius is 1, okay. Now the 4 roots, where are the roots located? Okay, let me show it in red. So pi by 4 is here, 3 pi by 4 is here, 5 pi by 4 is exactly here, 7 pi by 4 is here, okay. So now if you remember the contour that we had, the contour that we had looked like this. So it was A and it was like this. So this was our C0, which was of radius A, and we are going to take the limit as a goes to infinity. So a is so you can assume that a is greater than 1, okay. So basically only these 2 poles lie within this contour, within C0. So the poles that lie within C0 are basically I pi by 4 and 3 I pi by 4, okay. So then what I can write is that this I is, which is integral C 0 1 over 1 plus z power 4 dz is equal to residue at e raised to I pi by 4 plus residue at e raised to into 2 pi I. So, it is 2 pi I times residue at. Now, the residue at I pi, how do you calculate the residue at I pi by 4? Okay. For that, what you have to do is you have to factor this out. Okay. So, I can write my I as integral over C 0 1 over, I am going to take out. Okay. So, okay, let me evaluate. Okay. So, e to the I pi by 4 is equal to, now cos pi by 4 is 1 by root 2, sin pi by 4 is 1 by root 2. So, it is 1 by root 2 1 plus I. Okay. So, e to the I 3 pi by 4 is equal to, becomes negative 1 by root 2 minus 1 plus I, and just for completeness, e to the I 5 pi by 4 is equal to 1 by root 2 minus 1 minus I, and e to the I 7 pi by 4 is equal to 1 by root 2 1 minus I. Okay. You can easily verify these things, okay, by doing the cosine and sine. Okay. So, so then I can write my integral. Okay, so I can write 1 plus z power 4 is equal to z minus, okay, now e to the I pi by 4 is 1 by root 2 1 plus I z minus 1 by root 2 minus 1 plus I, and you have z minus 1 by root 2 minus 1 minus I, z minus 1 by root 2 1 minus I. Okay, so, these are the 4 roots. Okay, now actually we are not interested in these 2 poles, okay, because these 2 poles lie e to the I pi by 4 and e to the I 5 pi by 4 and e to the I 7 pi by 4. So, these lie outside the contour of interest. So, what we will do is we will just multiply this out. Okay. So, I will write this as z minus 1 by root 2 1 plus I, z minus 1 by root 2 minus 1 plus I. Okay. And so if you multiply this out, okay, you will get the following. So, you will get z square, okay, and then minus z by root 2 1 minus I minus z by root 2 minus 1 minus I plus 1 by 2, and you have minus 1 minus I and 1 minus I. So, I will write it as minus 1 plus I 1 minus I. Okay. So, if you multiply this out, what you will get is the following: z minus 1 by root 2 1 plus I, z minus 1 by root 2 minus 1 plus I, and now if you add up these two, so you have 1 minus I and minus 1 minus I. Okay. So, it will be minus 2 I. Okay. So, and then 2 divided by root 2 will give you root 2. So, and then minus and minus will give you plus. So, it will be plus, okay. So, I will write this as z square plus z root 2 I minus half. Now, 1 plus I into 1 minus I is same as 1 minus I square. Okay. So, 1 minus I square is 1 minus minus 1, that is 2. Okay, and I will just write this as minus 1. Okay. So, now what we have is we wrote this in this form. Now, you notice that this corresponds to the pole at e to the I pi by 4, this corresponds to the pole at e to the I 3 pi by 4. Okay. So, now we can use the residue theorem. Now, we can evaluate the two residues. So, we need the residue at e to the I pi by 4. So, if you want to calculate the residue at e to the I pi by 4, okay, then what you have to do is you can write this integral over the contour C 0 close contour 1 over 1 plus z power 4 dz is equal to 1 over z minus 1 by root 2 minus 1 plus I z square plus z root 2 I minus 1. We want this evaluated at, this whole thing evaluated at z equal to 1 by root 2. So, corresponding to the first pole. So, let me take the 1 over 2 pi I outside. Okay. 1 by root 2 1 plus I, okay. And in the next residue what you will have is plus 1 over z minus 1 by root 2 1 plus I z square plus z root 2 I minus 1. This evaluated at z equal to 1 by root 2 minus 1 plus I. So, we are almost done. Okay. So, now when I put z equal to 1 by root 2 1 plus I, okay, so I will get 1 by root 2 1 plus I and minus 1 by root 2 minus 1 plus I. Okay. So, the I terms will cancel. So, what I will get here is 1 over, okay, in the first term will become just 2 by root 2, that is root 2. The second term, now if I put z equal to 1 by root 2 1 plus I and I square it, okay, so that will give me square of this term. So, that is 1 by 2 and square of this is 1 plus I square is 1 plus I square is minus 1 plus 2 I, okay, which is just 2 I. Plus now z root 2 will just z root 2 is just 1 plus I into I minus 1. Okay, so, this is the first residue. The second residue is 1 divided by, now in this case I have to substitute z equal to 1 by root 2 minus 1 plus I. So, 1 by root 2 minus 1 plus I, okay, and again what you will see is that the I term will cancel. So, you will just have root 2. Okay. Now, z square in this case will give me I again. So, z square will give me 1 by 2, okay. This is 1 minus 1 will cancel and you have minus I, sorry. Okay. You have minus I and then you have z root 2 I will give me plus I minus 1 plus I minus 1. Okay. So, this is just, so if I have 1 by root 2, I have I plus I, that is 2 I, okay, and 2 I minus 2. So, and then I have 1 by root 2. Okay. Now, I minus I, so one of the i's will cancel, okay, and then you have plus I square, which is minus 1. So, I have minus 2. So, just check again. So, z square will give me I. Okay. So, this is basically your root, okay, and if you just you can simplify this, okay, and 2 root 2, okay, and you have 1 over I minus 1 minus 1. Okay. Okay. So, this is the basic idea, okay, and then I can write my integral. Okay. So, with this I can write my contour integral in the following way. So, integral over C 0 1 over 1 or integral, we can write integral minus a to a limit as a tends to infinity 1 over 1 plus x power 4 dx. Okay. This can be written as 2 pi I into 1 over 2 root 2, okay, and there is I think there should be an I plus 1 here. Yeah, this there is a factor of I plus 1. So, finally, what you get is you will just get a factor of I here, okay, and this will be just pi by root 2. Okay. So, finally, at the when you have done with all these calculations, you will get this kind of answer. Okay. But the important thing about this is the method that we used, okay, where we took our integral from minus a to a and wrote it as a closed integral, wrote it as the integral over the closed contour minus this integral over C, okay, and usually you will have I mean the kind of if your function is analytic, okay, then its integral will be 0, then the integral over the closed contour will be 0, okay. But if your function is not analytic, then it will have some poles, okay. So, then that function will have some power of x here, which will ensure that integral over the contour C goes to 0. These are the I mean these are the kind of problems that you can do using complex variables, okay. And so, I hope I have been able to show through this how you can use complex variables, okay, to evaluate integrals over real functions, okay. And so, I will stop this lecture for now, okay, and in the next lecture I will just recap what you have done and we will do some practice problems. Thank you.